Let's take some time to analyze some functions for vertical asymptotes and then determine whether or not those asymptotes approach positive infinity or negative infinity. We'll get to it. The first one is x squared plus 1 over x squared minus 1. So remember that a function has an asymptote if it's the quotient of two continuous functions and there is a point where the top function is not 0 and the bottom function is 0. So in every case here we've got a continuous function, continuous function, continuous, 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 continuous. So we have a lot of different functions. There are all the functions here are continuous. So since that's true, we can just analyze the numerator and the denominator. So in this particular case, x squared plus 1. What we notice for x squared plus 1 is that it is continuous, or it's a non-zero everywhere. It's a parabola shifted up 1, so it's never 0. So that tells me that anywhere where the denominator is 0 must be a vertical asymptote. So to do this, the easiest way in my mind is to factor. We'll say that that is x squared plus 1, x plus 1, x minus 1. So in doing this, we can see that there is a vertical asymptote at x equals negative 1 and x equals positive 1. But we need to analyze the behavior of this on the left and the right. So ultimately what we need to do is we need to take the left and right hand limit here, the left and right hand limit there. So let's think about that. So let's take the limit as x approaches negative 1 from the left of this function. So if it's negative 1 from the left, all you really need to do here is we're trying to determine if it's a positive infinity or a negative infinity. So the easiest way to do that is just to determine whether or not the numerator is positive or negative. If you can do that, you know you're going to an infinity, so we need to figure out if you're going up or going down. So let's think about this. If it's coming from the left of negative 1, so if negative 1's here, it's to the left. So think if it was just a little more negative than negative 1. So if I plug that number in here, think of it as like negative 2, for instance. If I plug in negative 2 in here, that's going to be a negative number because negative 2 plus 1 is negative. If I plug in a negative 2 over here, that's also going to be negative. So negative times a negative is a positive. And then up here, negative 1 squared is positive, plus 1 is positive, so we end up with positive infinity. Does that make sense? Similarly, so that now we're coming at negative 1 from the positive side. So think of it, if negative 1's here, it's a little to the right on the number line. So let's use a number like 0. So if I plug in 0 up here, I get 0 plus 1, that's positive. 0 plus 1 is positive. 0 minus 1 is negative. So I have positive, positive, negative. So that tells me that the left and right hand limits don't agree, that it's going up towards positive, down towards negative infinity. Over here, if I have positive 1 from the left, so again 1 is here, now we're coming from the left, so let's use that 0 again, right? We can use, if we know that it's 0, we can kind of cheat and reuse this one. We know that's negative infinity. And then finally, if we come at 1 from the right, if we come at 1 from the right, then let's pick a number like 2. That's positive, 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 positive infinity. So that's how we would do this for this particular type of problem. Sorry, I smudged that out. Let's keep on rolling. The second one's a little easier. We have 1 over 3 minus x. So this is never 0 on top. So this is only 0 when x is equal to 3. So what about this case? So it's approaching 3 from the left. So 3 is here from the left. So let's pick a number that's slightly smaller than 3. How about 2? So that's, if I was doing 3 minus 2, that's positive. So that tells me that this is positive infinity here. Similarly, if we do it from the right, let's pick like 4. 3 minus 4 is negative, so this is negative infinity. Let's keep on rolling. Have t squared minus t over t to the 4th minus 1. So let's do a little bit of algebra here. So we need to factor this. And we have to be a little more clever. This is something that you have probably seen before, but you probably haven't seen for a while. Well, hopefully that you've seen before, but this could be factored into t squared plus 1, t squared minus 1. It's because it's a difference of squares, but instead of a to the 4th power, because that's like t squared squared. It's probably a little difficult to think about, but it factors into that difference of squares. And then this continues to factor because it's also a difference of squares. So all of that. And what we notice is that both of them have a t minus 1 on the end. So that tells me that this is always positive. This is 0 at 0, but in this particular case, this one's 0 at negative 1. So that tells me that t equals negative 1 is a vertical asymptote. So let's figure out how this behaves to the left and to the right. Let's take the limit as t approaches negative 1. T over t squared plus 1, t plus 1. So from the left. So let's pick a number like negative 2. That's negative. Negative 2 squared is positive, so this whole thing is positive. So it's negative divided by a negative, because negative 2 plus 1 is negative. So that tells me that I approach positive infinity. Now I have to approach negative 1 from the right. And normally I'd say pick something like 0, but the problem is 0 is already taken, because if you try to plug in 0 here, that's gonna go away. So we need to get a little closer to the actual point. Now you could always pick really close numbers like negative 1.001 or whatever, and that's perfectly fine. And if you have a calculator, feel free to do this. But if you're trying to do this by hand, pick convenient numbers. Just make sure that you pick them somewhat close to the number you're looking for. So in this case, let's take something like, instead of being 0, maybe negative 1/2. So that's negative on top, positive, and positive. Because negative 1/2 plus 1 is still positive 1/2. So that tells me that goes to negative infinity. And you won't always have them swapping, but a lot of times you will have that behavior, but just not always. And finally we have this, sine of x minus 2 over x minus 2. So we have an issue because when I plug in 2 to the bottom, it's 0 on the bottom and on the top. So I can't just immediately determine whether or not this is a asymptote or not. So we have to be a little more clever, because the result that we had said if one's 0 and the other one isn't, rather this one isn't and this one is 0, then we're guaranteed an asymptote. But if they're both 0, we may still have an asymptote. We just might need to be, again, more clever about how we go about it. And in this particular case, we need to analyze the behavior. What this is if I have a function, let's call it f of x, sine x over x, then what this is this is f of x minus 2. So why am I doing this? Well, what this tells me is that this is just the same function as this one shifted over 2. That's all it's doing, shifting over 2. Now, if we go back and look at this very standard, well-studied function, if we go look at this standard, well-studied function, what we remember about that is its graph. We remember that at 0 it's here, and then it kind of bottoms out. So it does that. Now this one would be the same graph, but it would be shifted over 2. So you'd have something like that. So if those are the graphs, can we have a removable, or can we have any sort of asymptote here? No. What we have is a removable discontinuity. And we could apply that squeeze theorem here and show that it's shifted here. Now we'd have to be a little more rigorous and clever to really do it, but the idea is that if you have a good handle on what these graphs are, you can think of them in terms of shifts without having to analyze this. So what we find here is no asymptotes. And really, that's all you have to do.